Hi, this is our second video on electron configurations, and it is our 7th video in Unit 5. We should be experts at writing electron configurations now after class, but let's just remember that we're just describing the orbitals where the electrons are located in an atom, and we're doing this by giving the principal quantum number, we're giving the angular momentum quantum number, that L, which is S, P, D, and F, and then we are giving a superscript, which is the number of electrons in the orbital. All right, let's practice, and let's go ahead and write the electron configuration for bromine with 35 electrons. All right, we're going to use the alphabet order from lowest to highest energy, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, now we fill in the 3d10, and then it's 4p5. If we add all those superscripts up, we will come up with 35, the number of electrons in bromine. One note here, another method to write this would be to, when you're writing, to put the 3d prior to the 4s, and there are some advantages to writing it that way as well. I always tend to write it in the order that I fill the orbitals, and the 4s orbital is filled before the 3d orbital. Well, that was kind of long to write all of that. Is there a shorthand? And the answer is yes. And the shorthand method is using the noble gas that is prior to our element, and you place that symbol in brackets. So for bromine, our noble gas is argon, and you put it in brackets. And what that bracket means, it means it's the entire electron configuration for argon, and then we're going to start up where argon leaves off. So after argon, we're down to period 4, and we're in the S block. So argon 4s2, 3d10, and then 4p5. All right, so there we go. That's the shorthand method using the noble gas. Now this brings up a really important type of electron called the valence electrons. They're the outermost electrons in an atom, and they're used in bonding. They're the electrons that will be lost when we're forming cations and so forth. These are the outermost electrons, and they're the ones who do everything. All right, the valence electrons, when you have a total of 8 valence electrons, that is very stable. And so the noble gases have 8 valence electrons, and they're very stable and unreactive. The only noble gas that doesn't have 8 valence electrons is helium, but it's still a noble gas because its outermost shell is completely filled, and that's the 1s. So anyway, so valence electrons are the outermost electrons, and if you have 8 valence electrons, it's very stable, and 8 valence electrons is called an octet, and that's what the noble gases have, and that's why they're so unreactive. Alrighty, the rest of the electrons in the atom are called the kernel electrons. Well, now let's look at electron configuration of ions. What happens when you gain and lose electrons? Let's start off with an atom that loses electrons to form a cation. Well, which electrons do you remove? Well, the answer is you remove the outermost electrons, which are the valence electrons. So let's practice by writing the electron configuration for calcium. Calcium has 20 electrons, and so its electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, now looking at this electron configuration, the valence electrons are the electrons that are in the outermost shell in the highest number of n, so it's these 4s2 electrons. What is the electron configuration for calcium with a +2 charge, the calcium ion? Well, that means it has lost 2 electrons. The electrons that it has lost are the outermost ones, or these 4s2 electrons. So the electron configuration for calcium with a +2 charge is going to be 1s2, 2s2, 2p6, 3s2, and 3p6. Now, for an anion where electrons are gained, what's going to happen is you're just going to add an electron to the next available spot in our alphabet order. So let's go ahead and do chlorine. Chlorine has 17 electrons, so it's 1s2, 2s2, 2p6, 3s2, 3p5. Now, if we're talking about the chloride ion, so it has a -1 charge, we now have 18 electrons, and it's going to be 1s2, 2s2, 2p6, 3s2, 3p not 5, because we've gained an electron, it's going to be 3p6. Now, that brings us up to something called isoelectronic. And atoms and ions that have the same electron configuration are said to be isoelectronic. So what's the electron configuration for argon? Okay, so argon has 18 electrons. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Wait a minute, we just wrote that as the electron configuration for chlorine with a -1 charge. So this chloride ion and argon are isoelectronic. They have the same electron configuration. But let's name another ion that's isoelectronic with argon. That was calcium that lost 2 electrons. So calcium plus 2 and chloride with a -1, they both have this electron configuration. If you look back at your notes, they have the exact same electron configuration as argon. So argon, chloride, and calcium with a +2 are what we call an isoelectronic series. They all have the same electron configuration. Another new word, paramagnetism. Paramagnetic is a property when a substance has one or more unpaired electrons. A paramagnetic substance is drawn into a magnetic field. Now, something that's paramagnetic, we can only tell if we're looking at the orbital diagram. So let's go ahead and look at something like carbon. Let's write the electron configuration for carbon with our 6 electrons. 1s2, 2s2, 2p6. And you might, oh, whoa, 2p2, excuse me. I was on a roll there. All right, you might say, well, goodness, here's our 1s orbital and our 2s orbital, and 2p, remember we have 3p orbitals. So if we fill these electrons in, they're paired, that's the Pauli exclusion principle. But now, when we fill in this 2p, remember Hund's rule? It tells us to put 1 electron in each orbital before you go back and pair them up. Even though we have an even number of electrons, so you might think they're all paired up, they're not. We have 2 unpaired electrons, so carbon is paramagnetic. It has unpaired electrons. Okay, so you sometimes have to look at the orbital diagram to figure out if it's paramagnetic, but if they're all paired up, it's called diamagnetic. And that's when all the electrons are paired and they are slightly repelled by a magnetic field. And so let's look at our electron configuration for neon, a noble gas. So 1s2, 2s2, 2p6. Okay, 1s, 2s, 2p. Notice that I'm filling them in following Hund's and Pauli's rules, and every single electron is paired up. That's called diamagnetic. The noble gases are diamagnetic. Also, groups 2, the alkaline earth metals, are diamagnetic, and then group number 12 is also diamagnetic. All of their electrons will be paired up. So that is diamagnetic.